Good day, students. So welcome to part 5 of the Algebra 2 Trig Regents exam for June 2013. In this installment, we're going to be going over questions 21 through 27. All right, let's take a look at question 21. It says the log of 4m squared is equivalent to. So this involves the use of the properties of logarithms. Let's review that real quick before we do this problem. So if you have a product of two factors as your logarithmic argument, so log of xy, that can also be written as log of x plus log of y. Okay, it is a quotient, log of x over y. It can be written as log of the numerator minus log of the denominator. All right, and if you have a case where it's an exponent, log of x to the y. I'm sorry, I'm gonna write this log of x to the y. You can basically power down the exponent. Okay, and then this becomes y log x. All right, so these are the properties we're going to use to, actually we're just going to use the first and last to simplify this expression. All right, so let's do it. We have log of 4m squared. So first thing you have to note is that this square affects only the m. If it affected the 4, there will be a parenthesis around this quantity right here, but there isn't a parenthesis, so this square applies only to the m, so you have to be really careful. Alright, so we're going to use the product property of logarithms first, since we have a product here, to express this as the sum of the factors. Okay, so log of 4 plus log of m to the second power. Alright, now we're going to power down this exponent, power this down, so this is going to become log of 4 plus 2 log m. Okay, so this is equivalent to option, let's see, option number 3. Okay, let's move on to question 22. This involves the law of sines. So it says in triangle PQR, little p equals. Now, anytime you're dealing with the law of sines or any problem involving triangles, you want to give yourself a visual so you can ensure that you're labeling your triangles correctly. Okay, so let's say we have a triangle PQR. Now, the way that you label the angles doesn't really matter, so I can just call this P dot Q dot that's R, but you have to be really careful as to how you label these sides, okay? So if this is uppercase P, then the side opposite it will be lower p. If this is uppercase Q, then the side opposite will be lowercase q. If this is uppercase R, representing this angle, then the side opposite will be lowercase r. Okay, so what we're looking for is P. So we're going to be setting up our ratios using angle little p, using angle P, okay? And the side with little p. So remember, if you look at your reference sheet, the law of sines can be expressed as A over sine A equals little b over sine b equals little c over sine c. This enables us to compare these equations in different ways, okay? So we're looking for A, we compare with B or pair with C. All right, so to find little p, let's see the setups that we can come up with. So for the first one, how about we use the p's that we need and the r's, okay? So using that, we have little p over sine big P equals little r over sine big R. Now to get little p isolated, we'll multiply both sides by sine p on the left and sine p on the right. Okay, this divides out. So we have little p equals r sine big P over sine r. Okay, let's see, do we have a match here? Boom, absolutely, this matches with option 2. Alright, so there goes your answer. Had it been we picked Q, we'll end up with a correct expression, but it will not match any of these ones we have here. Okay, so there goes our answer, option number 2. Okay, let's shift our attention to 23. It says if tan of our cosine over 3 over k is equal to 3 over 3, then k is, this is a right triangle trig problem. So in order to get started, what we're going to do is make a sketch of the situation, okay? So we have some angle that when you take the tan of that angle, you get root 3 over 3, and that angle is equivalent to the arc cosine of root 3 over k. So let's sketch the triangle. Okay, it has to be a right triangle because we're dealing with right triangle trig here. That's what SOHCAHTOA applies to. So let's call this is the angle, okay, theta. So the argument of tan right here, this entire expression is theta. All right, now, what is tan? What we'll do is write SOHCAHTOA. What is TOA? So it tells me that tan theta is equal to opposite over adjacent. Okay? So in this problem, if this is a reference angle, that means the side opposite the reference angle is going to be my opposite. Okay? And this is going to be my adjacent. And then the other side opposite of 90 degrees will be my hypotenuse. Okay, so we know that tan of this theta, let's call this expression theta. Tan theta is root 3 over 3. But wait, tan is also opposite over adjacent, right? So if tan is opposite over adjacent, this tells me that the adjacent is 3 and the opposite is root 3. So let's apply that to our measure. So the opposite is going to be, this side is going to be root 3 and the adjacent is going to be 3. Okay? All right, now, let's see. We also have the equation that our angle theta is equal to arc cosine root 3 over k. So theta is equal to the inverse cosine of root 3 over k. So what does this tell me? It tells me that cosine theta is root 3 over k, right? How do I know? Well, to get this expression isolated, we can take the cosine of both sides. Okay, so you take cosine of theta equals cosine of the inverse cosine of root 3 over k. Okay, so since these two are inverses, they need to cancel each other out. So what we have is that cosine theta is equal to root 3 over k. But wait, what is cosine in SOHCAHTOA? Cosine is adjacent over hypotenuse. So this also tells me that root 3 over k is equal to adjacent of a hypotenuse. Okay, so if I can find out what the measure of the hypotenuse is in this right triangle, then I can figure out what this ratio is and then set the denominators equal to each other to get what the value of k is. Okay. All right, so let's see. How do we figure out the hypotenuse of a right triangle that we know this measure of the legs? Well, we'll label it. Let's call this A, call this B, and let's call this C. So what relates three sides of a right triangle? The Pythagorean theorem. So C squared is equal to A squared plus B squared. We all know that. So let's apply this formula to this situation that we're dealing with right here. So C squared, we don't know what C is as a hypotenuse, so I'm going to call it H squared is equal to A squared, which is the adjacent, so 3 squared plus B squared, which is root 3, the opposite. Let's simplify this. We'll have H squared equals 9 plus 3. H squared equals 12. So to get H, what we're going to do is we're going to take the square root of both sides. Okay? So we take the square root of both sides. You have, let's break it apart here. H equals root 12. Okay? How about we simplify that? So we have root 12. Break it down using factor tree. Take out 2, 2, 6, and then 2, 3. And then these two 2's come out as a 2. So it's going to be 2 rad 3 for your H. Okay? So now we have enough information to generate what ratio is equivalent to cosine theta. Okay? Alright, so let's go ahead and generate that expression. So we have, let's see, cosine theta is equal to root 3 over k. And that is also equal to the adjacent. The adjacent is 3 over the hypotenuse is 2 root 3. Okay, if you're confused, go back to the triangle. Remember we said the adjacent was 3 from TOA. And we just found the hypotenuse, which is 2 root 3. So adjacent of a hypotenuse, 2 root 3. Let's simplify this a little bit more. How about we rationalize the denominator? Okay, so to do that, we'll multiply top and bottom by root 3, root 3. So the right side is going to be equal to 3 root 3 over root 3 times root 3 is 3, so over 2 times 3. This 3's divide out, so you end up with root 3 over 2. Okay, so root 3 over 2 is equal to root 3 over k. Then it follows that what? K is 2. You can just cross multiply and divide by root 3. You can clearly see that k must be 2. Alright, so we can see that the answer is option number 2. Alright, so there you have it. Alright, let's take a look at question 24. It says, which expression is equivalent to 2x to the negative 2, y to the negative 2 over 4y to the negative 5? So we're going to be using the reciprocal property of exponents to do this. Any term that has a negative exponent needs to be reciprocated in order to invert the negativity of that exponent, okay? So we have 2x to the negative 2, y to the negative 2, over 4y to the negative 5. Okay, so this x has a negative exponent, this y also, and this y on the bottom. So we're just going to reciprocate them to compensate for that sign, okay? So we're going to have 2. This y to the negative 5th comes to the top, as y to the 5th becomes positive, over x square y square. Okay? All right, now we can simplify the y's. Remember, when you're dividing exponents of the same base, you subtract the exponents, right? So this becomes 2y. What I'm going to do is subtract the smaller from the bigger. Okay, so 5 minus 2 over x squared. Okay, and then that simplifies further into, well, there's a 4 right here. Let's not forget that. Put the 4 there. 4, and we have 2y to the third over 4x squared. And we can also simplify 2 and 4. 2 goes into itself once, and 2 goes into 4 twice. So the final result is going to be y to the third over 2x squared. Okay, so our answer is option number 1. All right, let's take a look at 25. 25 says express with a rational denominator and in simplest form, x over x minus root x is. So we need to get rid of this radical component of the denominator. So we have x divided by x minus root x. Now, to do this, we have to convert these two into squares. To accomplish that, we're going to take advantage of the difference of squares formula. We're going to create the difference of squares by multiplying the numerator and the denominator by the conjugate the conjugate of this denominator right here. Alright, so what's the conjugate? You just simply invert the middle sign. So instead of x minus root x, you have x plus root x on the bottom and x plus root x on the top. Okay? Alright, so now we're just going to multiply. If you multiply the top, well, let's leave the top alone as it is. So we're going to have x times x plus root x. I'm not going to FOIL it out. And then in the denominator, if you FOIL this out, first you have x squared. Outer, you have plus x root x. Inner, you have minus x root x. And then last, you have minus root x squared. Okay? Alright, so this simplifies into x times x plus root x, and in the denominator over x squared. Now these two in the center cancel out, as we should expect, because we're multiplying the difference of two like terms. So you end up with the difference of your squares. So it's going to be x squared minus now root x squared. The square and the root cancel out, so you're left with minus x. So we're going to have x times x plus root x. And then in the denominator, we'll factor out an x. So we have x minus 1. Okay? Now we can divide out the x's on the top and the bottom. X goes here 1, and x goes here 1. And then your final answer is going to be x plus root x divided by x minus 1. All right? So you see that the answer is clearly option 4. All right, let's move on to shift our attention to question 26. 26 says, what is the common ratio of the sequence? This is a geometric sequence. You remember the formula for the common ratio of the geometric sequence. If you have a geometric sequence, the common ratio is given by a2 divided by a1, or you can do a3 divided by a2, just an divided by an plus 1, a term divided by the term before it, okay? All right, so this is a1 right here, and then this is a2. So to find the common ratio, we're going to do a2, which is negative 3 over 32, a to the third, b to the fourth, and then that is going to be divided by 1 over 64, a to the fifth, b to the third. Okay? All right, so how do we do this? Well, what we can do is deal with the fractions separately and then do the exponents next, okay? All right, so now when you're dividing fractions, you multiply the numerator by the reciprocal of the denominator, right? So I'm going to write this as negative 3 over 32 multiplied by the reciprocal of 1 over 64, which is 64 over 1. That takes care of a fraction. So when you divide into fractions, you multiply the fraction of the numerator by the reciprocal of the fraction of the denominator. Okay? All right. Now for this, I'm going to use the law of exponents to simplify this variable. So what I normally do is I subtract the exponent of the smaller one from the bigger one, and the variable stays where the bigger exponent is. For the a's, we have 3 and a 5. The bigger one is in the denominator, so the denominator rules or wins. So you're going to subtract the smaller exponent from the top from the bigger exponent on the bottom. If you look at the b's, the power in the numerator is bigger, so b on top wins. So what you do is just subtract the exponent of the smaller, which is 3, from that of the bigger. Okay? All right, now let's simplify this right here. We'll divide 32 goes here once, 32 goes here twice. When you multiply those two, you have negative 6. 4 minus 3 is just 1. Negative 6b divided by a to the second power. All right? So you can clearly see here that our answer is option number 2. All right, let's take a look at question number 27. It says in triangle KLM, KL is 20, LM is 13, M and measure of angle K is 40. Find the measure of angle M. All right, so let's go ahead and do this. All right, so let's take a look at this problem. So in this case, in this problem, we're going to have to use either the law of sines or law of cosines to find its angle. But if we're using the law of sines to find an angle, then there might be an ambiguity in the solution, okay? So just keep that in mind. Anytime you're looking for an angular measure, there could be an ambiguity in that situation, okay? So let's see if that's the case here. So first thing we're going to do is draw a triangle and label it completely, okay? So it doesn't really matter how you draw it, just make sure that your measurements are consistent. Let's see. All right, let's try it again. So let's label our triangle. So we have to be really careful here. So this is K, L, M. KL is 20. LM is 13. The measure of angle K is 40. All right, so we asked find the measure of angle M. So to find M, let's call that big M. We're going to use the following law of sines proportion. Okay, so we're going to say sine of big M over see sine of big M over KL, which is little m, okay? Because you know if this is big M, this side right here is little m, right? And then if this is big K, this is little k. Now, which other ratio am I going to use? Well, the next ratio I have to use, the next fraction I have to use, I need to know the measures of both the sides and the angle, all right? L, I cannot use L because I do not even know even one of the measures, neither the side nor the angle. But K meets that expectation. I have both the angle and the side. So we're going to use sine big K over little k, okay? I have the big letters on top here. In the other example, I had the small letters on the bottom. It doesn't really matter. I like to go with what I'm looking for. If I'm looking for the angles, I have the angles on top. If I'm looking for the sides, I have the sides on top. Okay, whichever way you set it up, it doesn't matter. Just make sure that the denominators and the numerators are consistent in terms of it being sides or angles. Okay, so to find the sine m, let's plug in the measures. We have a sine of big M over little m, which is 20, equals sine of 40 over little k, which is 13. All right, so multiply both sides by 20. Multiply by 20. Multiply by 20. Put the 20 over here so they get confused. These two divide out. So sine m is going to be, let's plug this into our calculators and see what we'll get. So we have 20 sine 40 over 13. Let's make sure our mode is in degrees first, or else we'll get a wrong answer. Okay, put in degrees, enter. So we have 0.9, 98, let's 0.9889. Okay, so that's 0.9889. Okay, so what we're going to do next is take the inverse sine of both sides to isolate m. So the inverse sine of sine m equals the inverse sine of 0.9889. Okay, so that gives us what m is. Let's see what we get. So we're going to go second function inverse sine of our previous answer. We got 81.45. Okay, now note this result is the value of m, and this angular measure is the reference angle. Okay, so the question is, if you consider the quadrants that sine is positive, if this is a reference angle, are there more than one result that satisfies this expectation? Okay, that's the question. So we have m as 81 degrees. Is there another equation that satisfies it? So remember that this is your reference angle. So let's go ahead and take a look at the sketch. The two angles where sine is, the two quadrants where sine is positive is quadrant 1 and quadrant 2. Okay, if this is 81 degrees, that the possible solutions that we have 81 degrees here and 81 degrees here. Okay, these are the values that satisfy since it's positive, and we know sine is positive in quadrants 1 and 2. So if this is 81 degrees, can we have a complete triangle here? We know that if this is 81 degrees, then the measure that satisfies that will be this remaining piece right here. How many degrees is that going to be? To satisfy the expectation is going to be 180 minus 81. So we have 180 minus 81, which is 99 degrees. Okay, so now the first one is 81, or the second one is 91. The question is, can these two work for the triangle? Is it possible for these two angles to work? We know that one angle is 40, so if I add 40 to these two triangles, if the sum is less than 180, then it works. But if the sum is less than 180, the one that violates that. If the sum is more than 180, then the sum that violates that will be eliminated. Okay? So we have one angle is 81, one angle is 91. If we put in the 40 degrees there, does it work or does it not work? That's the question. Okay? So let me make two sketches for you and see if both triangles make sense. All right, so let's do this. All right, so let's say we have one side right here, and then so this is your 40. Let's say this is your 40-degree angle. So this is 40 right here, 40, and this is 40. So the question is, do these two answers work, or do none of them work? So the first one is 81 degrees. Let's put it in. So we say that's angle M. Kind of change the orientation of my triangle a little bit. Pardon me. So angle M is 81. Does this make sense? If I add these two angles, do I get something? Do I still have enough left for here? Or is your sum less than 180? That's the question. Remember, the sum of angles in a triangle is equal to 180. Okay? So 81 plus 40 is 121. Does that make sense? Absolutely, because 180 minus 121 is 59. So we still have enough room for another angle. So this is good. All right, so we know we have at least one solution here, so that's perfect. How about 91 though? Does that make sense? Let's complete the triangle and see if that makes any sense. So if this is 40 and if this is 91, have we exceeded or met the 180-degree limit? If we exceed 180, then it makes absolutely no sense. Okay, so let's see. 40 plus 91. We have 131. Does that make sense? Absolutely. Since 131 is less than 180, we still have room for the last angle. So if we go 180 minus 131, you get 49 degrees. So that makes perfect sense. So this angle also works. Okay? So this is 59 degrees and this is 49 degrees. So since we have two answers that actually work here, what does that tell me? It tells me that the measure of angle M is ambiguous. Okay? Measure of angle M is ambiguous. So you just have to remember that anytime you're taking the inverse sign, you must check to make sure that the angle in quadrant 2 and the angle in quadrant 1, both that satisfy the inverse of that angle actually makes sense. If both of them make sense, then you have an ambiguous case. If only one makes sense, then that will be your correct answer. In this case, both of them make perfect sense because they add up to 180. So we have an ambiguous case as our final result. All right, so there you have it.